In this video, we're going to continue doing some examples of solving application problems that involve rational equations. And in this video, we're going to focus on what I call distance, rate, and time problems. Now, distance, rate, and time problems are easy to identify because in the problem, we're going to be given distances, rates, or speeds, and times. In this example, we're told a plane flies 620 miles. There's a distance. With the wind in the same amount of time it takes to fly 430 miles, there's another distance, against the wind. If this plane flies at a rate of 217 miles per hour, there's a rate. What is the speed of the wind? So we're looking for a rate. And we're told to round to the nearest whole number if necessary. So these problems are easy to spot. The hardest part of these is setting them up correctly. And you may notice that I already have a table below with 4 columns and 2 rows. Anytime I'm working a distance, rate, and time problem of this nature, I always go ahead and set up my table. Here's why. We know that distance is equal to rate times time. So I'm going to use the second column for my distance values, the third column for my rate values, and the fourth column for my time values. My first column is going to be reserved for my scenarios. And in these types of problems, we'll always have 2 different scenarios. In this problem, we have one scenario where the plane is flying with the wind, and we have one scenario where the plane is flying against the wind. So I'll let the top row be all of my values for when the plane is flying with the wind, and we'll let the bottom row be all of the values for when the plane is flying against the wind. All right, so let's go ahead and go back to our problem now and start picking out information and plugging it into our table. The first thing that I notice is that the plane flies 620 miles with the wind. That value is obviously a distance, and it's in our with the wind category. So we would plug in 620 as the distance that the plane flies with the wind. The next thing I notice is that we're given the value of 430 miles, which is a distance, and that's how far the plane flies against the wind. So 430 will be our distance in the against the wind category. Now this is where we have to use a little bit of intuition. We're told that the plane flies at a rate of 217 miles per hour in still air. That means that if there's no wind at all, this plane can fly at 217 miles per hour. But in our 2 scenarios, the plane is not flying in still air. It's either flying with the wind or against the wind. When a plane is flying with the wind, that means it's flying with the wind at its back. In other words, the wind is adding to the speed of the plane. So when we're flying with the wind, the speed is 217 miles per hour. Plus ever how much the wind is pushing us, because the wind is adding to our speed because we're flying with it. Well, we don't know how fast the wind is moving or by how much it's adding to our speed. That's an unknown. So let's let W be the speed of the wind. And that works out perfect for us because the question that we need to answer is, what is the speed of the wind? And traditionally, what we're looking for, if it is unknown, that's what we define our variable to be. So our rate flying with the wind is 217 plus W, because our speed will be faster than 217 miles per hour because the wind is pushing us. Likewise, our speed against the wind would be 217 minus W. Because if we're flying against the wind, we're flying into the wind. In other words, we're flying in the opposite direction as the wind. And when that's happening, the wind is actually taking away from our speed. So our rate flying against the wind would be 217 minus W. Now, other than the information we've already put into our table, I don't see any other information given to us in the problem. But that's okay. Because when we're flying with the wind and against the wind, we already have our distance and our rate, or our speed. That's all I need to find the time. Because if distance equals rate times time, and I need to find the time associated with that distance and rate, then I can divide both sides of this equation by r to get t by itself. Dividing the left side of this equation by r gives us distance over rate equals, and dividing the right side of the equation by r gives us t. So we know that the time associated with flying with the wind and against the wind is equal to the distance over the rate. So the time flying with the wind has to be equal to the distance flown over the rate, which would be 620 over 217 plus w. And the time against the wind would be 430 over 217 minus w. Now we have every aspect of our table filled in. But if we want to find w, the speed of the wind, we have to have an equation to solve. So let's look back up at the information that we're given in our problem. Did they give us some sneaky information, some sneaky way of setting up an equation? And of course they did. We wouldn't be able to solve this problem without it. They tell us that both of these trips, with the wind and against the wind, took the same amount of time. That means that the time flying with the wind and the time flying against the wind have to be equal to one another. So that gives us this equation, where the two times are equal. Now the great news about this is a proportion. One fraction equals one fraction. So we can solve by cross multiplying. The first cross product is 620 times the difference 217 minus w. And that has to be equal to the second cross product, which is 430 times the sum 217 plus w. The first step to solving this equation is to simplify both sides by distributing. On the left, 620 times 217 is 134,540, and 620 times minus w is minus 620w. And that's equal to, on the right, 430 times 217 is 93,310, plus 430 times w, which is 430w. Now let's begin solving by combining like terms. Let's add 620w to both sides of this equation. On the left, that'll give us 134,540. And that's equal to, on the right, 93,310 plus 1,050w. Now let's subtract 93,310 from both sides to isolate 1,050w. Subtracting 93,310 from both sides of the equation gives us 41,230 on the left side and 1,050w on the right. Now let's divide both sides of the equation by 1,050 to solve for w. Dividing 41,230 by 1,050 gives us 39.2666666 and so on. But we're asked to round to the nearest whole number. Rounding 39.26 to the nearest whole number is 39. So the speed of the wind is 39 miles per hour. Let's do one more example that's very similar to the one that we just did. Here we're told a fisherman travels 9 miles downstream with the current in the same time that he travels 2 miles upstream against the current. If the speed of the current is 7 miles per hour, what is the speed that the fisherman travels in still water? Notice in this example that we're given distances, rates, and times. So this is a distance, rate, time problem. And we'll start it just like we did our previous example. Notice in this example that our two different scenarios are a fisherman traveling downstream and then upstream. Now notice pretty quickly that the problem tells us that the fisherman travels 9 miles downstream and he travels 2 miles upstream. And we're looking for the speed that the fisherman travels in still water. That means with no help from the current. So that's what we'll define our variable to be. We'll let S be the fisherman's speed with no current. Or another way to say that is his speed in still water. So we know that S is going to be part of his rate traveling downstream and upstream. Now if we're traveling downstream, that means we're traveling with the current, which means that the current is adding to our speed. And the current is adding 7 miles per hour to our speed. So traveling downstream, our speed or our rate will be S plus 7. Traveling upstream, When we're traveling against the current will take away from our speed. So our speed going upstream will be s minus 7. Now remember from our first example that if we have a distance and a rate, we automatically have a time, because time is equal to distance over rate. So the time spent traveling downstream is 9 over s plus 7, and the time spent traveling upstream is 2 over s minus 7. Now again, just like in the previous example, what do we know about these two times? We know that the time spent traveling downstream is the same as the time spent traveling upstream. So again, the two times must be equal. So 9 over s plus 7 has to be equal to 2 over s minus 7. And this is the equation that we need to solve for s. Solve by cross multiplying. That gives us 9 times the difference, s minus 7, is equal to 2 times the sum, s plus 7. Now let's distribute on both sides of the equation to remove the parentheses. That gives us 9s minus 63 on the left and 2s plus 14 on the right. Now let's add 63 to both sides of the equation to isolate 9s on the left. That gives us 9s equals 2s plus 77. Now let's subtract 2s from both sides of the equation to combine our s terms. Subtracting 2s from the left side of the equation gives us 7s, and subtracting 2s from the right side gives us 77. Now divide both sides of the equation by 7 to isolate s, and that gives us s equals 11. Now remember, s is the fisherman's speed with no current. So here s is a speed, which means that the fisherman with no current can travel at 11 miles per hour.